So let's understand the concept of ownership in the Rust programming language. So ownership is Rust's most unique feature and has deep implications for the rest of the language. It enables Rust to make memory safety guarantees without needing a garbage collector. So it's important to understand how ownership works. In this chapter, we'll talk about ownership as well as several related features, borrowing, slices, and how Rust lays data out in memory. So let's go over here and we'll go right here, which is what is ownership, and let's read this. So ownership is a set of rules that govern how a Rust program manages memory. So basically, it's a set of rules that tells how to manage the memory for the Rust language. All programs have to manage the way they use a computer's memory while running. Some languages have garbage collection that regularly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory, like C language and C++. While in in Java, you would have a garbage collector. Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks. Okay, if any of the rules are violated, the program won't compile. None of the features of ownership will slow down your program while it's running. Because ownership is a new concept for many programmers, it does take some time to get used to. The good news is that the more experience you become with Rust and the rules of the ownership system, the easier you'll find it to naturally develop code that is safe and efficient. Keep at it. When you understand ownership, you'll have a solid foundation for understanding the features that make Rust unique. In this chapter, you'll learn ownership by working through some examples that focus on a very common data structure, which is strings. Now, the stack and the heap. Many programmers or many programming languages don't require you to think about the stack and the heap very often. But in systems programming like Rust, whether a value is on the stack or on the heap affects how the language behaves and why you have to make certain decisions. Parts of ownership will be described in relation to the stack and the heap later in this chapter. So here is a brief explanation in preparation. So we're going to have this kind of explanation, but let's just have the ownership explained a little bit right here. So what it says over here, first let's take a look at the ownership rules. Keep these rules in mind as we work through the examples that illustrate them. Each value in Rust has an owner, okay? Got it? There can only be one owner at a time, okay? When the owner goes out of scope, the value will be dropped. So variable scope. Now that we're past basic Rust syntax, we won't include all the main function. We will not include the main function in code in examples. So if you're following along, make sure to put the following examples inside a main function manually. As a result, our examples will be a bit more concise, letting us focus on the actual details rather than boilerplate code. So we're not going to look into the main function. We're going to have to take care of that by ourselves. It's not a problem at all. As a first example of ownership, we'll look at the scope of some variables. A scope is the range within a program for which an item is valid. Take the following variable. This is a let s is equal to hello. The variable s refers to a string literal, and where the value of the string is hard-coded into the text of our program, the variable is valid from the point at which it's declared until the end of the current scope. Now, it says over here, listing 4.1 or 4-1 shows a program with comments annotating where the variable s would be valid. So you can see over here, let s is equal to hello. S is not valid here. It's not declared yet. And when it's over here, it's s is valid from this point forward. Do stuff with s. This scope is now over. So right after this, you see this squiggly records. The scope is now over, and s is no longer valid. So basically, they're telling you what scope is, remains valid until it goes out of scope. The string type, telling you what a string type is, right? And what kind of string can be mutated. So we have this kind of string, and then we're trying to change it. So what kind of string can be mutated? Over here we have a string from hello, and we have s. Then we have push. We're trying to put world inside. Push underscore stir appends a literal to a string, and then we have the s. This will print hello world. So let me run this, and if you look into this, So you can see you could print hello world. So what's the difference here? Why can string be mutated but literals cannot? The difference is in how these two types deal with memory. So strings can be mutated while literals can't. Okay. Okay, let's go ahead and move forward. Memory and allocation. It's just telling you how memory is allocated, variables and data interaction with move. So using variables can interact with multiple variables can interact with the same data in different ways in Rust. Let's look at an example using an integer. So we have 5 and then we have y. Okay, over here we have probable. We can probably guess that what this is doing, bind the value of 5 to x, then make a copy of the value in x and bind it to y. We now have two variables, x and y, and both equal to 5, right? That's what we assume. This is indeed what is happening because integers are simple values with a known fixed size. And these two 5 values are pushed onto the stack. Now let's take a look on the string version. So we're trying to put hello, right? So we have string from, and we have hello, we put in S1. And then we try to do S1 to S2. This looks very similar. So we might assume that the way it works would be the same. That is, the second line would make a copy of the value in S1 and bind it to S2. But this isn't quite that. What happens? Take a look at figure, this figure, to see what is happening to string under the covers. A string is made up of 3 parts, shown on the left. So basically a pointer, a len, and a capacity. Okay, that's what a string is made up of, and we have a name and a value. So, so we have a pointer to the memory that holds the string is made up of 3 parts, shown on the left. A pointer to the memory that holds the contents of a string. So this is the contents, basically a pointer, a length, and a capacity. This group of data is stored on the stack. On the right is the memory on the heap that holds the content. So basically the stack is this, but the heap has the index 0, 1, 2, 3, 4, and we have this hello string value. But the thing is, representation in memory of a string holding the value hello bound to S1. Now this is bound to S1. The length is how much memory in bytes the contents of the string are currently using. The capacity is the total amount of memory in bytes that the string has received from the allocator. So this is 5 bytes. Okay. Now the thing is, the difference between length and capacity matters, but not in the context. But not in this context. So for now, it's fine to ignore the capacity. When we assign S1 to S2, the string data is copied, meaning we copy the pointer, the length, and the capacity that are on the stack. We do not copy the data on the heap that the pointer refers to. In other words, the data representation in memory looks like this. So we're basically saying S1 and S2, remember? We're trying to basically copy, we do not copy the data on the heap that the pointer refers to. So we basically, in other words, the data representation in memory looks like this. So we have S1 and S2 pointing to the same heap. So representation in memory of the variable S2 that has a copy of the pointer, length, and capacity of S1. This representation does not look like figure this, which is what memory would look like if Rust instead copied the heap data as well. If Rust did this, the operation S2 is equal to S1 would be very expensive in terms of runtime and performance if the data on the heap were large. So, yeah, right? So earlier we said with that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for the variable. But figure 4-2 shows both data pointers pointing to the same location. This is a problem. When S2 and S1 go out of scope, they will both try to free the same memory. This is known as double free error and is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. To ensure memory safety, after the line let S2 is equal to S1, Rust considers S1 as no longer valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. It won't work. So basically, S1 is equal to hello, and then S2 is equal to S1, and then try to use S1, it's not going to work. It's going to say, you'll get an error like this because Rust prevents you from using the invalidated reference. So it says over here that borrow a moved value S1, so you cannot use it, right? And if you've heard the term shallow copy and deep copy while working with other languages, the concept of copying the pointer length and capacity without copying the data probably sounds like making a shallow copy, right? So basically, copying the concept of copying the pointer length and capacity without copying the data probably sounds like making a shallow copy, but because Rust also invalidates the first variable instead of being called a shallow copy, it's known as a move. In this example, we would say that S1 was moved into S2. So what actually happens is this. So basically, S1 is basically moved into S2 and no longer valid now. Yeah, S1 is invalidated. This solves our problem. With only S2 valid, when it goes out of scope, it alone will free the memory, and we're done. In addition, there's a design choice that's implied by this. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. So that basically sums up that concept here: variables and data interacting with clone. So essentially, we're trying to have a string S1 which has hello, trying to copy it S1.clone to S2, and then when we try to run both of these things, so we say S1 and S2, but we assume that we have both hello, and that is good. That is actually good. That works just fine and explicitly produces the behavior, right? When the heap data gets where the heap data does get copied. When you see a called clone, you know that some arbitrary code is being executed, and that code may be expensive. It's a visual indicator that something different is going on. And we have stack only data. So essentially, we're trying to copy from the stack here. For ints, it's going to work, right? But this code seems to contradict what we have just learned. We don't want to call to clone, but x is still valid and doesn't move to y. The reason is that types such as integers that have a known size at compile time are stored entirely on the stack, so copies of the actual values are quick to make. That means there's no reason we would want to prevent x from being valid after we create the variable y. In other words, there's no difference between deep and shallow copying here. So calling clone doesn't do anything different from the usual shallow copying, and we can leave it out. So this is basically it. And ownership and functions, the mechanics of that passing a value to a function are similar to those when assigning a value to a variable. Passing a variable to a function will move or copy. Okay, passing variable to a function will move or copy just as assignment does, and listing 4-3 has an example with some annotations showing where variables go into and out of scope. So over here we have this function, and you just have to understand what's going on in here, return values in scope. So what essentially happens here is that we have a let s string from hello. S comes into scope, right? After that we have takes ownership s. This is basically a function we created right here. And this essentially gets the string, and some string comes into scope, and then it just prints the string out. That's it. Here some string goes out of scope, and drop is called, the backing memory is freed. And then we have makes copies. But one thing is that s's value moves into the function, and so is no longer valid. Here basically s is gone after that because it just drops out. Let x is equal to 5. X comes into the scope, and then after that makes copy x would move into the function. So basically over here we have an i32. Some integer comes into the scope, println some integer. After here some integer goes out of scope, nothing special happens. So after that what we have is makes copy, but i32 is copy, so it's okay to still use x afterwards. So I believe you understand. Here x goes out of scope because it's out of this squiggly brackets, then s, but because s's value was moved, nothing special happens. So essentially that's the concept of ownership here, and we basically would sum it up. Hopefully I would explain it later on with more detail in our next upcoming videos, and if you have any good explanations regarding this, you could also write it down in the chats for this video. So thank you, and keep watching Coding Cleverly.